All right, so we're now moving on to the next part of this unit, and that's going to be nonlinear graphs. So we're now going to focus on functions and graphs that are not just straight lines like we have been doing. All right, and we're going to focus on two in particular, and that's going to be absolute value and quadratic. All right, so we're now going to learn how to graph these. What you're going to have to know by the end of this video is, first off, what is a parent function? Because when we graph these absolute value and this quadratic graph, we're only going to learn how to graph the parent function right now. All right. After that, you're going to have to know how to graph, like I said, absolute value and quadratic functions. And then we're going to learn a new one as well, which is not going to be a parent function. It's not one of these basic graphs, but it's going to be a different kind, which is called a piecewise function. So at the end of this video, you're going to learn how to graph three new different things. The parent function of an absolute value and quadratic graph, and then you're also going to have to learn how to graph a piecewise function. All right, so let's just go ahead and get started on this video. All right, so first off, what is a parent function? That's what we have to know. And a parent function is the most basic, simplest version of any given function that must pass through the origin on a coordinate plane. So we've already learned one kind of function, and we've learned f of x is equal to a linear graph. And the parent function of a linear graph is simply f of x is equal to x. There's no plus or minus being happening to this. So that means our y-intercept in this case is actually equal to 0. And our slope in this would be equal to 1. So it's not anything beyond just a basic graph. All right, this would pass through the origin of 0, 0, because if x is 0, y would be 0 in this case. And you see there's nothing being multiplied to it, nothing being added or subtracted. So it is the most basic version of this function. All right, and when we learn how to graph quadratics and absolute values, we're going to first learn how to do that with just the parent functions. And then we're going to talk about, well, what happens when we want to, or when we need to move this graph around, or when we get these different kinds of graphs, like we know how to graph f of x is equal to 2x minus 3. We know how to graph that. So we're going to learn how we can apply these parent functions to teach us how to graph more complex functions. All right, and let's go ahead and get started then on graphing the most simplest basic versions of first a quadratic and then an absolute value. All right, so a quadratic function is where we have x squared. So when we have a power of 2 to our variable, it is now a quadratic. Before, when we had a power of 1, y is equal to x, that let us know it was linear. Now when we see that it is x squared, that tells us that it is quadratic. All right, we can write this as f of x is equal to x squared as well, but I'm just going to focus on just y is equal to for right now instead of focusing on it in function notation. All right, just some characteristics. A quadratic equation or a quadratic function. Its graph is a U-shaped graph. The name of this is a parabola. And this point here, where the graph stops and turns around and gives us our symmetrical version of this U, that is called our vertex. And when we're normally graphing quadratics, that's the most important point for us to identify. But in the parent function, it's really easy. All right, so when we go to graph this in the most basic form, what I'm going to teach you now is by using a table. All right, we can always just pick points and plug it in. The problem is, because this graph is a U-shaped, we need to make sure that we are finding or identifying this vertex. Because if we don't identify that, we may pick all points that just happen to be on the right-hand side of the U, and we don't know where the other part of the U is. So we must find what's called that vertex, because that's what creates our graph or separates it into two symmetrical parts. Well, the good thing and the lucky thing is when we're dealing with our parent function, our vertex is the point 0, 0. All right, so now once we identify that vertex, we need to pick 2 points on both sides because I know that this graph is going to be a U shape on both sides. So I need to pick 2 points that are on to the right-hand side of my vertex and 2 points on the left-hand side. So this way I can verify the symmetrical value and I know exactly how this graph is going to look. When you're picking these points, just make sure that you are being consistent. So I'm going to pick -1, and since that's 1 unit away from my vertex, I'm going to pick another one that's 1 unit away in the other direction, which is a +1. I'm going to pick -2, so I'm going to also pick +2 because they're both 2 units away from that vertex. Once we actually learn how to graph this a little bit better, a little bit easier, and it feels more comfortable, we only actually have to pick one side of our vertex, and we can use the symmetrical properties to fill in the rest. But we're going to be doing 2 from both sides. Right? And then from here, to figure out what our y value is, well, if we know what x is, I can plug it in to figure out what y is. So in this case, y is going to be equal to negative 2 squared, which is equal to 4. So when x is negative 2, y is 4, and it generates the order pair of negative 2 comma 4. Our next one, y is then equal to negative 1 squared, which is equal to positive 1, because it's negative 1 times negative 1, and 2 negatives times each other is a positive. And that gives me the order pair of negative 1, 1. Then I'll go ahead and do the next one. I don't need to do 0, 0, because we already know that. And then I'll plug it in, y is equal to 1 squared, which is equal to 1 as well. So it gives me the point 1, 1. And then my last one, y is equal to 2 squared, which is equal to 4. So it generates a point 2 comma 4. So once I have these 5 points, I can then plot them on my graph and graph them. So I'm going to go ahead first. I'm going to plot my vertex in red. So this 0, 0, I'm going to plot this one first. And then I'm going to go ahead and plot the other ones in black. All right, so we have negative 1, 1. We have negative 2, 4. We have 1, 1, and 2, 4. When we're graphing these, we're actually just doing like a quick little sketch because it's going to be pretty much impossible for you to perfectly draw that U to match up all those decimal values. So we're just going to make sure it just has this U-shaped. And then when we go ahead and draw it, just give it a quick little sketch to give it that end of that U. Some teachers will have you stop your arrows here before you go and reach that next X value, because that way they can say that they know that what you're doing there is accurate in the sense that you're not showing that 3 is a different value. But for me, if you just have that U-shaped and those 5 points are accurate, that is good. All right, now, this point here, this red, is called our vertex. And when we learn to translate this graph, because this is just the parent function, the most basic version of it, it passes through the origin, and when we go to graph more complex versions of this, we need to know where that vertex is. So it can move. It can go to the right, it can go to the left, it can go up, it can go down. It can move around this graph. It doesn't have to be at our origin. So that is the most important thing for us to be able to find. All right, the vertex. That is the point where our graph stops and turns around. And if we were to draw, let me erase these little arrows. If we were to draw a line going down here, passing through our vertex, you see this gives us a symmetrical graph, meaning that it is if I were to take those two sides and fold them on top of each other, if I can imagine it's paper, that those two parts would form just one side of that U. All right, it is perfectly symmetrical. All right, so that's what you need to know about this graph. All right, you're going to find when we do the absolute value, it is almost identical. It's almost the same thing. It's just it's not a U-shaped, it's a V-shaped instead. All right, so now let's go ahead and go over our absolute value. But this is what you need to know for your quadratic. When you're graphing, just pick the point 0, 0 for now because we're only dealing with the parent functions. And then pick 2 points that are less than 2 points that are greater than. Make sure we're consistent in how far away those points are from 0 so we can verify that it's symmetrical. And then we can just go ahead and plot those points on our graph and draw the U-shaped. All right, so now let's go ahead and do our absolute value. All right, so now we're going to learn about our absolute value graphs and functions. This graph is a V-shaped graph. So because it's almost the same shape as a quadratic, they have a lot of the same characteristics. So it's going to be symmetrical, and we have to find that vertex as well, which I'm going to put in red. And remember, our vertex is that point where our graph stops and turns around. So it would be this point here. So we do need to still find our vertex, all right? And it is a V-shaped graph. It doesn't have a name like parabola like that. So this is just pretty much what you need to know about absolute value. So the same thing holds true when we're doing absolute value. When we're doing the most basic version of this, we're going to learn first to create a table. And then that 0, because we know that it passes through 0 and our origin of 0, 0, that we can put in the middle of our graph, just like with our parabola and our quadratic. Just like with that, in the most basic parent version function of this, the vertex is our origin 0, 0. So this is going to actually be our vertex. Just like with the other one, we're going to pick 2 points that are less than and 2 points that are greater than, wanting to be consistent with where we're picking them, just so we can verify that symmetrical value of it. Just like with the other one, we're going to plug it in. Y is equal to the absolute value of negative 2, which is equal to positive 2, which generates the ordered pair of negative 2, 2. Then we'll plug in y is equal to negative 1, absolute value of negative 1, which is positive 1. So now it gives us the absolute value, or the ordered pair, of negative 1, 1. This vertex, which I'll put in red, gives us the point 0, 0. Then we're going to plug in y is equal to the absolute value of positive 1, which is equal to 1. So it gives us the ordered pair 1, 1. And then the last one is going to be where x is equal to 2. So the absolute value of 2 is also equal to 2. And it generates a point of 2, 2. Once again, once we have these, we just go ahead and plot them. I'm just going to plot my vertex in red just so we can identify that. And the rest I'm just going to plot in black. So we have negative 2, 2, negative 1, 1, 1, 1, and 2, 2. So we see each one of these points is falling in that corner of that box. So if we just imagine this right-hand side, this will have a slope of 1, which gives us that more like direct straight line, which is why it has that V shape instead of that U, because they're actually growing all at the same rate. Where when we had our quadratic, since the number is being squared, they're not growing at the same rate because 3 squared is 9, 2 squared is 4. So the difference between that 3 squared and 2 squared is 5, whereas the difference between 2 squared and 1 squared is 3. So you see we're not increasing at the same rate. It's not an arithmetic sequence like we were just learning. So therefore, it's not going to have that U shape, but it'll be more direct path, meaning it's going to give us that V shape. So then from here, let me go ahead and make sure I'm in drawing. So for here, I can then draw my graph going from both sides. And there is my absolute value graph. It has a V shaped. Same thing as before, this is symmetrical. So if I were to draw a line going through my vertex, I see that the graph is the exact same replica on the right-hand side as it is on the left-hand side. So it is symmetrical. If I were to fold this and think of it being on paper, it will give me a straight line. All right, once again, this is the most basic version of an absolute value graph. This is the parent version of it. Nothing's being added, nothing's being multiplied to it. It is just strictly the absolute value of x. All right, we are going to learn in class how we can translate these graphs, and what that means is move them around, because graphs don't always just pass through the origin, as we know with our linear equations. We don't always just graph y is equal to x, and matter of fact, very rarely do we. So we need to make sure that we can understand how to graph more complex versions, and we're only going to learn it at a very basic level right now, where we're just going to talk about how we can translate them around. All right, how we can move them about. And when they're moving, how we know where the vertex is from that to allow us to then plot our vertex point and pick the points on both sides to ensure that symmetrical shape. All right, now we're going to go into a piecewise function. All right, so now when we see this graph, this is called a piecewise function, or piecewise graph, or piecewise. All right, when we see this, something should jump at us that this is a little bit different, because we have that brace and they're giving us two different equations. They're giving us negative x minus 4 and they're giving us x. And next to it, it says if x is less than 0. And next to here, it says if x is greater than or equal to 0. So we know that x represents our domain. So when we see these two different parts of x, it's telling us that depending on what our value is for x, that is the graph or function that we use. So if x is 0 or greater than 0, we would just simply use that equation, y is equal to x. If x is less than 0, then we're going to use that top equation of negative x minus 4. So we actually have two different graphs here that we have, two different equations. And depending on what our domain is, that's going to tell us which domain we would use. So if I say, hey, x is equal to 8, well, we would then use that blue graph and say y is equal to x, because that domain falls in that range of being greater than 0. And if I say x is equal to negative 5, well, that means we are going to use the equation y is equal to negative x minus 4, because negative 5 would fall in that domain. So depending on what we're using, we then or what number we're using, that determines what equation we're using. So I'm just going to color this. If we were to look at this order at this coordinate plane, all of these x values, because these are all negative, would satisfy or be working for that yellow equation. And all of these values we would use for that blue equation plus when x is 0. So that y-axis, when x is 0, we would also use. So this is actually telling us that we have two different functions, two different equations that we're using within this one problem. And depending on what domain we have, that's the graph that we need to use, or that is the equation that we need to use. So now I'm going to erase this and we're going to talk about graphing this. And when we graph this, the first point that we have to graph for either of these, so I'm just going to write y is equal to negative x minus 4. Above it, I'll say x is less than 0. Y is equal to x, and above it, I'll say x is greater than or equal to 0. The first point we have to plot is that point here that they actually share. So it's that value that's separating our domain. So the reason why we have to do that is because this point is actually going to be separating our graph and kind of creating a boundary, almost like we did with the inequalities. So I'm just going to put a dotted line here just to represent that on that line, we need to represent these two graphs. So I will first plug them in. So if x is 0, that means y is equal to 0. If x is 0, that means y is equal to negative 0 minus 4, or y is equal to negative 4. So I'm going to plot these 2 points of 0, 0, and 0, negative 4. But we need to think about this. All right, this is where the things that we learned in the past come back. This one includes 0. Well, how do we show in an inequality that we include it? With a solid circle. This one does not include 0 because it's just less than, not equal to. Well, in inequalities, how do we represent something that is not included? With an open circle. So you see, everything we learned before is coming back now. I'm going to actually change the color of this just so that this way you understand which one is which. So let's go ahead and highlight this instead of yellow. Let's highlight this as green. So this way when we see the green graph, we know we're referring to that equation. And then when we see the blue graph, we know we're referring to that one. So when I go to graph this, I'm going to plot the point 0, negative 4. However, it needs to be an open circle because it's saying that we will use all the way up as close as we can to that point, but not that point. And then from there, I can graph this one of two ways. I can just graph it as negative x minus 4, identify my slope as negative 1, and then I can go ahead and plot the next few points. However, I can't plot any points to the right of this because these are all positive x values. And once we go to positive x, we're actually going to be using the other equation. So I need to just graph it to the left. So since going to the left is negative, I'm going to actually think about this as a positive 1 over negative 1 for my change in y over change in x, because I need to go up and to the left, up and to the left, up and to the left. Or I can just pick points and plug them in. I can say, well, x is equal to negative 1, so y is equal to negative of negative 1 minus 4. Y is then equal to 1 minus 4. Y is equal to negative 3, so I have the point of negative 1, negative 3. And once I plot that point, all we need is 2 points to draw our graph. So now I'm going to go ahead and draw this graph going through there. So that green graph represents this green part of our piecewise function. Then the next part is we need to graph the blue one. So now we have our domain is x is greater than or equal to 0. Y is equal to 0. Y is equal to x is our equation for that part. We already said when x is equal to 0, y is also equal to 0, so we have the point 0, 0. This needs to be a colored in circle because we're representing this value counts for that. Now I can either graph y is equal to x. My slope is 1, so I know that this is going to be up 1 over 1, up 1 over 1, so my graph will look like this. Or if I don't want to do it that way and I want to make sure I'm getting it right, I can say, well, when x is 1, y is also 1, and I'll plot the point 1, 1, and draw my line going through those 2 points. And this is our answer, and this is our graph to the piecewise function. So we see that our blue domain is representing any number that's 0 or greater than, and that's why this graph stops and ends there. Right? It doesn't go any further than that. Our green graph does not include the 0. That's why we have the open circle, but it can't go to the right because we're only including the negative numbers. So this would be our graph. If we try to do our vertical line test, we see that this passes. So in our piecewise function, we actually have like 2 separate problems that we're doing and 2 separate graphs that we're doing. And then we just have to make sure that we're plotting that boundary point properly, that one of them could be colored and the other one could not be colored. Both could not be colored as well, because we could have a function that says where x is less than 0, we use this, and when x is greater than 0, we use this. It doesn't have to be one of them's colored, but if it's a function, both of them can't be colored, because if they're both colored, then that gives us 2 y values for x, which means it can't work. All right, that is it for this video.